Hi everyone, and welcome back to the channel. Today, we're diving into something powerful, a key concept found in almost every real-world automation system. PLC, timers, the software-based solution for precise time control. In this video, we'll focus specifically on Siemens S7-300 PLC timers and how they work in real projects. Forget the old, bulky hardware timers. With PLCs, all your timing logic happens inside the software. It's smarter, faster, more reliable, and easier to maintain. But do you really understand how timers work in automation? From simple machines to complex factory lines, timers are essential for handling delays, sequences, and safety operations. Before we dive into the theory of timers, let me show you a simple animated example to help you understand how they work. In this project, imagine that I've written a program and downloaded it to a Siemens S7-300 PLC. I'm using this animation style to make the tutorial more exciting and easier to understand for everyone. It's just like a real project, and after introducing each timer, I'll use these animations to show you how they work in real-world hardware situations. In this example, we have an electrical motor and two push buttons. For safety reasons, we don't want the motor to start immediately after pressing the start button. Instead, we want the PLC to wait 10 seconds and then start the motor. Let's simulate this now. Watch the animation. The start button is pressed, the timer begins counting, and after 10 seconds, the motor turns on. This simple delay is handled by a PLC software timer, and this is exactly what we'll be learning about in this video. In traditional control panels, this would require a physical timer, extra wiring, and more time for configuration. But with a PLC, the same result is achieved using just a few lines of code faster, cleaner, and easier to troubleshoot. Every PLC comes with a set of built-in software timers. The exact number depends on the model. For instance, certain Siemens S7-300 PLCs support up to 512 timers, whereas higher-end CPUs in the same series can handle 1024 or even more. The Siemens S7-300 PLC includes 5 types of software timers, each designed for different control needs based on your project requirements. Pulse timer, extended pulse timer, on delay timer, retentive on delay timer, off delay timer. Each of these timers serves a specific purpose. Let's begin by explaining the inputs and outputs of the timers. All S7-300 PLC timers use the same inputs and outputs. The main difference is how and when they act. The first input is the start input. When this input is activated, the timer begins counting, except in the case of the off delay timer, which works differently. I'll explain that exception shortly. The second input is TV, time value. This is where we define how long the timer should count. We enter the time using the S5T format, which I'll explain in the next slide. The third input is the reset input. When this input is activated, the timer turns off even if the time has not finished. To activate the timer again, the start input must be re-triggered. The first output is Q timer status. It indicates whether the timer is currently active. The behavior of this output depends on the type of timer being used. For example, in some timers, Q turns on immediately when the input is triggered, while in others, it only turns on after the preset time has elapsed. The second output shows the remaining time in integer format. You can assign this to a memory word and use it inside the PLC program. The third output also shows the remaining time, but in BCD binary-coded decimal format. This format is useful for connecting to HMI displays, where you want to show the countdown in a readable number format. So now we've covered the inputs and outputs of Siemens timers. Let's look at this sample program. It's written in ladder logic, which is one of the programming languages supported by Siemens PLCs. In this program, I124.0 is used as the start input. When it's on, the timer activates and starts counting. The TV input is set with a time value in S5T format. I124.1 is used as the reset input. The output is assigned to Q124.0. When the timer is active, this output turns on. The BI binary integer and BCD outputs are not used in this tutorial, but I'll cover them later when we focus on timer monitoring. For now, just know that you can assign memory words to them and display them on your HMI if needed. In Siemens S7-300 PLCs, timers use a special time format called S5T to define the time value. The S5T format allows the PLC to understand exactly how long the timer should run. The general structure looks like this: S5 T# AH, BM, C, S, D, MS. Here's what each part means. AH hours. Replace A with the number of hours, then add H to indicate that the value is in hours. Example: S5T2H means 2 hours. BM minutes. Replace B with the number of minutes, then add M to indicate minutes. Example: S5T15M means 15 minutes. CS seconds. Replace C with the number of seconds, then add S to indicate that the value is in seconds. Example: S5T10S means 10 seconds. D, MS milliseconds. Replace D with the number of milliseconds, then add MS to indicate the value is in milliseconds. Example: S5T250MS means 250 milliseconds. Examples: S5T5S, 5 seconds. S5T2M30, S, 2 minutes and 30 seconds. S5T1H15M, 1 hour and 15 minutes. The minimum time value you can define in S5T format is 10 milliseconds. The maximum time value is 9,990 seconds, which equals 2 hours, 46 minutes, and 30 seconds. If you ever need to define a longer time duration than what S5T allows, you'll need to use IEC timers instead. Now, I've got a task for you. because just watching isn't enough. If you really want to learn PLC programming, you need to practice with your own hands. So go ahead, open SIMATIC Manager and create a new project. Then, go to OB1, insert any timer from the timer folder. It doesn't matter which type for now. The purpose of this task is simple. Just practice how to define a time value using the correct format. After inserting your timer, define a time value using the S5T format, for example, S5T10S for 10 seconds. Once you've done that, drop a comment below. Was it easy? Or did you run into any issues? If you couldn't do it or had any trouble, don't worry at the end of this video. I'll practice everything in SIMATIC Manager to make this tutorial even easier to understand. So make sure to watch until the end. The first timer we're going to discuss is the Pulse Timer SP. The Pulse Timer activates its output for a fixed preset duration. When the start input becomes true, the timer output Q turns on immediately. It stays on until one of two things happens. 1. The preset time value expires, or 2. The start input is turned off before timer finishes counting. This latter program was created in a simulation environment, and it's the same as what you would create in SIMATIC Manager, which we discussed in earlier lessons. I'm using simulation here to help you clearly see how each timer works in action. It behaves just like a real PLC program, so let's test it and see how the pulse timer operates. First, I'll turn on the start input to show what happens. As you can see, when I trigger the start input, the output Q turns on immediately, and the timer starts counting. In this program, I've defined the time value as 10 seconds. As you can see, it's written in S5T format like this, S5T10S. Once the preset time finishes, the output turns off even though the start input is still active. Now let's test another situation. I activate the start input again, but this time I turn it off before the timer finishes. As you can see, since the start input was deactivated early, the output also turns off immediately the timer stops, and the set time does not complete. Imagine the previous ladder logic program using the pulse timer has been downloaded to the PLC. In this program, I want the motor to run for exactly 10 seconds when I press the start button, even if I keep holding the button down. Let's test it. As you can see, when I pressed the start button, the PLC started counting and the motor kept running until the timer finished. This is a typical real-world application of the pulse timer, useful when you need a fixed output duration, regardless of how long the input stays active. Now let's move forward and explore the extended pulse timer, which gives us even more control over output timing and behavior. The extended pulse timer, written as SPEXT, works very similarly to the pulse timer but with one important difference. When the start input is activated, the timer output Q turns on immediately and stays on for the preset time. However, unlike the standard pulse timer, the start input does not need to remain active during the timing period. Once the timer has started, the output will stay on until the time expires, even if the start input is turned off. If you want to cancel the timer during the countdown, you can use the reset input. When the reset input is activated, the timer immediately stops and the output turns off. Let's test this timer. First, I activate the start input, and as you can see, the output cue turns on immediately. Then, I turn the start input off, but the timer continues running until the preset time expires. This demonstrates the key feature of the extended pulse timer. It doesn't require the start input to remain active during timing. Now, I activate the start input again, but this time, before the time finishes, I activate the reset input. As you can see, the timer stops immediately and the output turns off, even though the time wasn't completed. Let's move on to the next slide and test it in the simulation as well. Let's imagine I've already downloaded this ladder program to the PLC. Now, I'm going to test it. I press the start button and then release it. As you can see, the motor starts running and the timer begins counting down. After the full 10 seconds have passed, the motor turns off automatically. The key point here is, even though I released the start button right after pressing it, the PLC continued running the motor until the preset time expired. Now, let's try another scenario. I press and release the start button again, but before the timer finishes, I press the stop button. As you can see, the motor immediately stops, even though the timer was still counting. Now here's a challenge for you. Open SIMATIC Manager and try to write this exact program yourself. Here's your task. Define a 1-minute time value for the extended pulse timer. Start the simulation, and when the timer reaches 30 seconds, toggle the start input off and then on again. Observe what happens and write your result in the comments. Let's continue with the on-delay timer. In the pulse timer and extended pulse timer, when we activate the start input, the output turns on immediately and stays on until the preset time expires. But in some projects, we need the opposite behavior. We want the output to turn on after a delay, not right away. That's where the on-delay timer comes in. Here's how it works. When the start input is activated, the timer begins counting. Once the preset time has passed, the output turns on and it stays on as long as the start input remains active. If the start input is deactivated, or if the reset input is triggered, the timer resets and the output turns off. Let's test the on-delay timer. I've inserted the on-delay timer and set the time value to 10 seconds. Now I activate input I124.0, the start input. As you can see, the timer begins counting, but the output remains off while the timer is running. Once the 10 seconds are complete, the output turns on and stays on as long as the start input remains active. The key point here is that the start input must stay active for the output to remain on. If I deactivate the start input, the output turns off immediately. And to activate the timer again, I need to re-trigger the start input. Now let's move to the next slide and test this on-delay timer in the simulation. In this example, when I press the Start button, the PLC will wait exactly 10 seconds, and then it will start the electric motor. So, imagine I've already written this program and downloaded it to the PLC. Now let's see how it works. I've pressed the Start button, and the timer is now counting. The PLC is waiting for the 10-second delay to send the command to start the motor. Now, the motor is running, and it will keep running as long as I hold the Start button. Once I release the button, the motor will stop. Let's continue with the retentive on-delay timer, also known as SODTS in Siemens PLCs. The retentive on-delay timer works almost the same as the regular on-delay timer, but with one key difference. In both timers, when the start input is activated, the timer begins counting. Once the preset time is complete, the output Q turns on. But here's the key difference. In a regular on-delay timer, the start input must remain active the entire time. If it turns off before the time finishes, the timer resets. In a retentive on-delay timer, the start input only needs to be triggered once. You can turn it off, and the timer will continue counting until the defined time expires. After the full time has passed, the output turns on and stays on until the reset input is activated. I have inserted the retentive on-delay timer, and now I want to test this project. First, I trigger the start input. The timer begins counting. After the preset time finishes, the output Q turns on and stays on until I activate the reset input. And because this timer doesn't require the start input to stay active, I turned it off after starting the timer, and as you can see, the timer continued running. Let's move on to the next slide and test this timer again. I first press the start input and then release it, and the timer begins counting. As you can see, after the timer finishes counting, the output becomes active and stays on. Now, I'll press the stop button. Let's see what happens. I've pressed the stop button, and as expected, the PLC output deactivates and the motor stops running. We've finished covering both on-delay timers. Finally, let's take a look at the off-delay timer, the last timer in the Siemens S7-300 family. It works differently from the others, and it's very useful in specific automation scenarios. Let's see how it behaves. Off-delay timer, S-off DT. The off-delay timer works a bit differently from the others. When the start input is activated, the output Q turns on immediately. When the start input is deactivated, the timer begins counting down the preset time. The output stays on during this countdown and only turns off after the time expires or the reset input is activated. Let's test this timer. I activate the start input I124.0 and the output turns on immediately just as expected. Then I deactivate the start input. Now, the timer begins counting down. After the preset time finishes, the output turns off automatically. As you can see, the off delay timer is perfect for situations where you need to keep something running after the input signal turns off, like cooling systems or fans. Now, let's test another case. I activate the start input again, and the output turns on immediately. Then, I deactivate the start input, the timer starts counting down. But this time, before the countdown finishes, I activate the reset input. The output turns off immediately, even though the time had not yet expired. This shows how the reset input can interrupt the countdown and immediately stop the output, giving you full control when needed. Let's test it in the simulation. I press the start input. As you can see, the PLC immediately commands the output to turn on and keep it active. The timer is now ready to begin timing. Then, I deactivate the start input B, and the timer starts counting down. After the preset time expires, the output automatically turns off. We've now seen the last timer, and that means we've covered all of them. Each one is simple to understand and insertably useful in real automation projects. Up to this point, we've covered the theory behind each timer. Now it's time to move into practice. Let's open SIMATIC Manager and start working with timers directly inside the real Siemens S7-300 programming environment. Before we move on to SIMATIC Manager, I have a challenge for you. Open the SIMATIC Manager program and create this simple project. Imagine you have one light, a start button, and a stop button. When the start button is pressed and released, the light should blink on and off every second for 1 full minute. After 1 minute, the blinking should stop, and the light should stay constantly on until the stop button is pressed. Once you're done, let me know in the comments. Were you able to complete it? Did you run into any problems or need help? Pause the video now, try building the project, and then continue watching. If anything is unclear, feel free to go back and rewatch the earlier sections. This is a very important and practical skill in real automation projects. And don't forget, if you need help, I'm here to support you every step of the way. In the previous video, I already explained how to create a new project in SIMATIC Manager and complete the hardware configuration step by step. To save time in this video, I'll go straight to OB1 block and begin programming. If you're not familiar with those steps or you're having trouble, just go back and watch the previous video. I've explained everything clearly there. To select the required timer from the program, open the timer folder in the Program Elements section, also known as the instruction tree. Once you open the folder, you'll see all 5 types of S7-300 timers. Pulse, Timer, S-Pulse. Extended Pulse Timer, S-Pext. On Delay Timer, SODT. Retentive, On Delay Timer, SODTS. Off Delay Timer, SOFF DT. To insert a timer, Click on the network where you want to place it. Then either double-click the timer or drag and drop it into the program. I've inserted an SODT timer into Network 1. Now, we need to define its inputs and outputs. Start input. Add a normally open no contact and assign it the address I124.0. Time value TV. For this example, I want the timer to delay for 20 seconds, so I'll write S5T20S. Reset input. Again, insert a normally open contact and assign the address I124.1. With the inputs done, now it's time to assign a timer number. Timer numbers in S7-300 PLCs start from 0 and go up, depending on how many timers your CPU supports. For this project, I'll use T50. So I simply type T50 as the timer number. Lastly, we'll use the Q output of the timer. Insert a coil and assign it to Q124.0. This will turn on when the timer completes its delay. Let's test this timer in the SIMATIC Manager simulation. First, I open the simulation window. Then, I change the connection protocol to PLC Sim MPI so it connects properly to the simulated CPU. To make things easier, I also go to the View menu and select Always on Top. This keeps the simulation window visible above all other windows. Now, it's time to download the program to the simulation. Once the program is downloaded successfully, I run the CPU, and then I activate the start input to test how the timer behaves. As you can see, the timer is counting down. During this time, the output remains inactive and it will only turn on after the full time has passed. Once the time finishes, the output is activated and stays on as long as the start input remains active. Everything I explained earlier in theory works exactly the same way here in the SIMATIC Manager program. As you can see, it's simple and practical. Now you can apply it to any project based on your needs. Finally, let's insert an off delay timer and test it as well just for more practice. I've inserted a new network, and now I want to add an off delay timer SODT to this network. Let's configure the inputs and outputs. I've defined the start input at address I124.2. I've set the time value to 20 seconds S5T20s. For the reset input, I'm using address I124.3. And for the output, I've assigned Q124.1. Now let's download the program and test it in the simulator. First, I activate the start input. And as expected, the output turns on immediately. Then, I deactivate the start input, and the timer starts counting down from 20 seconds. Finally, once the timer finishes, the output also turns off. That's exactly how the off-delay timer works. Simple, useful, and easy to implement in real projects. Today, we covered all 5 types of timers in the Siemens S7-300 PLC, including how they work, how to configure them, and how to test them both in theory and in the SIMATIC Manager program. As you saw, timers are powerful, flexible, and essential tools in real-world automation projects. Whether you're just getting started or looking to strengthen your skills, mastering timers is a big step toward becoming a professional PLC programmer. If you followed along, let me know in the comments. Did everything work for you? Did you face any challenges? Don't forget, I'm here to help. Ask your questions and I'll do my best to support you. If you found this video helpful, please like, share, and subscribe to support the channel. And hit the bell so you won't miss the next lesson. We've got even more practical PLC tutorials coming soon. Thanks for watching, and I'll see you in the next video.